Okay, good morning. So we were about to complete today the next module, that is ride dynamics, part of our vehicle dynamics. We are going to have these two periods. In the first period, we are going to look at what is titled, the topic is road characterization. Road characterization. So how do you bring in a real road input to your vehicle model and you get your response? This is what we are going to study in the first period. And in the second following period, you are going to look at the design aspects of suspension for your ride primarily. So these are the two titles of today's two lectures. I'm going to share my screen to begin with my lecture. So if you are able to see the screen, I just have, as usual, now taken in the screen, the last lecture what we have seen. Just briefly, quickly, we'll look at it, and then we'll go ahead with doing today's class. So in the last class, we just have learned what is known as a pitch and bounce model of a vehicle body and for its natural behavior. So we had this coupled equation and we had a trial solution in steady state condition, and that has given you this determinant equating to 0, the characteristic equation of the system. So this is the study of what called free vibrational study. But it is of a coupled system. So you have both the motion bounce by Z and pitch by theta coupled. If that is so, how do you find the natural frequency of the system? Is what has been given by finding the roots of this characteristic equation of the system. And we had these two roots given by omega n1 and omega n2 for bounce and pitch respectively. And we have further discussed what would happen in case you have to use this wisely for understanding more physical insight of understanding concept of oscillation centers, which is given by Z is equal to L theta, L naught theta. So we were able to follow, there will be one oscillation center out of the wheelbase and another one will be falling within the wheelbase. When the system is uncoupled, then what would happen is one which is outside would go to a distance of infinite, and another one which is inside a wheelbase will come and coincide with the CG location and so on, which was result in poor ride quality. So we understood that we require a coupled motion of both of them in a system when it is designed, and also if it is designed for equal and dynamical system concept, that would result in very good quality ride. So that's what we have seen, where your vehicle body mass happens to be equivalent to the system, where I have two masses at front suspension connection, rear suspension connection, and then having stiffness of the front is slightly smaller than that of the rear. That would get a good ride comfort, is what we have witnessed in this slide. And continued with that, we just have revisited the very first part of ride dynamics lecture. There are three main objectives. One is to understand the vibration behavior of a vehicle and its nature through vehicle models. So we have, of course, started looking at description of full car model by 7 degree of freedom model, and we have learned in detail quarter car model and pitch and bounce model. And then we were to look at what does this human response to vibration and associated comfort boundary levels by SAE standard or ISO standards. And today's class is going to complete the third part of the main objective of our ride dynamics, that is characterization of surface irregularities. So if you look at the human response to the vibration to understand, there are many tests that are being carried out. One is a traditional test in any OEMs. You see that they conduct subjective ride measurements. And then they would also have some laboratory experiment on shake tables or ride simulator test, or they go to the test track with the vehicle and then with the necessary sensors mounted in a vehicle, and then they do a real-time ride measurement in the vehicle. So these are the various aspects of measurements that go in primarily that would give the determination of human tolerance for the vibration. And that's what we were looking at in the last class. The subject right measurement, always correlating it to the quantitative or objective measured data in the real-time road condition, is what is now current research people are working on. What is called objectification of vehicle data, right, to subjective ride data. So you see there are advanced techniques called neural network techniques, falls under the category of artificial intelligence. That would be a more viable solution, to have this correlation study of what does that is reported by a jury who are well trained, and his word is accepted as it is. He says this vehicle is good, that's good. He says this vehicle is not good, that's something, a problem to be looked at. And that would go into the people's hand of test engineers and researchers in the laboratory. And they do have many real-time data, which are called raw data, with their techniques of algorithms applied. They try to correlate and find out why that rating was like that. So what is that to do with the vehicle, and so on. So this is the kind of loop where OEMs are striving for improving their vehicle for its ride comfort. And other tests in the laboratories are the shake table test, can be at the subject level in a test bench like this, or can also be a real vehicle on the post with this kind of latest 6 degree of freedom shaker table, where subject can be in a real vehicle and the road inputs can be brought in here, and then you can have the measurement. But however, these are going to have some limitation, as it is not going to really account the real-time environment of the driving of your vehicle, and that's where you required, of course, this ride simulator test. These are in the laboratory performed, would give you to have an insight into influence of your vehicle on different road profiles or on different environmental conditions, but still they are in the laboratory. And that's where you see the real-time experiments like this, which are there on the road. And this is one such experiment. We were doing it with an ISO 2631 standard to meet measurement in the vehicle at 4 different locations. One at the seat location with 3 accelerometers of the driver, what is he perceive actually when you drive at the different speeds this vehicle. Another one at the seat rail, so that we will know what is the input that comes to the seat, and that is getting transferred to this occupant. So such kind of sophisticated, advanced, high-end instrumentations and equipments are necessary for whole body vibration of passenger car. Many of the OEMs have got, many of the premier institutions have got. As we also have at VIT, this credit goes to my professor, learning from him a lot, and then on the similar facilities, that is why we are able to develop at our university as well. So this is one such real-time measurement made for the MTech student project. So this is all what we have seen in the last class in order to look at this type of standards to understand. So these are giving the guideline, SAE J6A ride and vibration data manual. Gives you this range of frequencies from 1 Hz to 60 Hz in 3 domains, up to 6 Hz and 6 to 20 Hz and 20 to 60 Hz. With this values of jerk, acceleration or velocity to be constant, you have this plot where on y-axis you have amplitude of vibration, displacement amplitude as function of this, and you have to have your displacement amplitude felt by the vehicle should be below this line in order to have a comfort boundary met. I just have put the same diagram on this because of the clarity here. It's very well. You may also go through this from the textbook, Theory of Ground Vehicle by Wong, and why these values are constant in these ranges, and then that helps you to calculate what would be the displacement amplitude. When I say jerk, it is going to have relation with its amplitude. Jerk equals amplitude times omega cube, circular frequency cube. So if the excitation frequency chosen 2 and substitute that correspondingly, you would get what would be the displacement amplitude, and that should fall below this line of your vehicle. So this is that one standard from SAE for comfort is concerned. Similarly, you also had other standards from ISO for the frequency range 1 to 80 hertz with this three segregation here again. You have many stacking of these curves from 1 minute till 8 hours, which represent the variation of RMS acceleration in X direction, Y and Z direction. What are measured through what are called the seat pad accelerometer, which you have seen in our earlier slide from the road test. And those data should be falling below this line. If I drive my vehicle for one metropolitan to other metropolitan, say for more than 8 hours, then the average values of my this RMS acceleration should fall below this line in order to have there are three important levels by ISO 2631 called an exposure limit, fatigue or decreased proficiency boundaries or reduced comfort boundaries. So this is commonly used fatigue or decreased proficiency boundaries are this. And if you have to go for exposure limit, that only give a priority for the safety and health, not more of vibration aspect. Then whatever this is existing can be lifted up by 6 dB level. You could see on this y-axis. Similarly, if it is for reduced comfort boundaries, that means the comfort would be certainly ensured in high-end vehicle, then this would be lowered by 10 decibel level down, and you will have the same graphs. So on my left, what I have is the acceleration perceived by a driver or occupant from foot to head in vertical direction. So it's AY, and on the right, whatever I have is AX and AY, which is from back to chest or from side to side acceleration level. So you can see that as the exposure time increases, the boundary levels reduces. So if it is of 1 minute exposure, okay, that acceleration allowable will be more. Whereas if it is of a long drive, you see that the boundaries are dictated by lower curves. And this is what way you have to understand these standards. And as we do measurement of a vehicle ride accelerations perceived by human, it should fall below this. In fact, it should fall below this scale 10 dB level down push for reduced boundary condition, boundary comfort boundaries. Then it would be very good, which most of the autonomous vehicle are focusing now, that you get into your vehicle, instruct your vehicle to take you to a office. You have a nice infrastructure. Your vehicle is going to take you autonomously. You don't require to drive. You can read, write, and eat in the vehicle and do your work without any worry. So that's the future autonomous vehicle that we talk on today. Definitely cannot compromise with the ride quality requirement in your vehicle. So this is what you understand from these standards, and let's now go into, this is what we finished in the last class, and we will now go into understand how do you characterize your road profile. That's what is my first lecture objective. So this is lecture number 15, and we are in ride dynamics part, and we are going to look at vehicle ride dynamics for random excitation. See, these are the vehicle models so far that we have seen. I just have summarizing here in this page. So you see the 7-degree freedom model, and you have your pitch and bounce model of your sprung mass, and you have your quarter car model of your sprung and unsprung mass. Again, 2-degree freedom model accounts only the bounce. And you have this, which we have not discussed. You may go through that from Josser textbook of vehicle dynamics. Where you have here half car model, where you have two unsprung mass, their bounce and the body bounce and roll model. So like pitch and bounce of body alone you have seen. If you take the body alone, pitch and roll and bounce can be looked at without considering this. Analogous this way, only the wheelbase is replaced by track length. Otherwise, mathematically, if you look at it, is same, and the textbook notations are different. You should not get confused with them. You should comfortably, gracefully accept them, and as you go through this particular model. And when I account here this unsprung mass also, that is not going to change your result. That's going to become more and more realistic as you eliminate the assumption of wide separation of frequencies. In this case, we consider. and you would be able to carry out. But however, if you look at the bounce, pitch, and roll. So this is the order of annoying. So bounce is less annoying than pitch, pitch is less annoying than roll. They all will fall within 1 to 2 hertz. And the order, if you look at in a typical car, bounce frequency is lower than that of pitch, and pitch natural frequency is lower than that of roll, right? So this is all why did I put this all? This all we have studied under the category called deterministic model. So what do you mean by deterministic model? We have given a well-known harmonic excitation. Instead of looking at here the road random profile, we have given a harmonic excitation we have studied, and that's why it's called a deterministic model. And those model is very good model for comparative study of your vehicle ride comfort of different brands or on a different road. But it is for a parametric study, it is good. But however, the real sensation of a human perception to measure, you have to really account your road, real road. And the real road is no more can be described by a deterministic model. So what I mean by deterministic model, again, you see harmonic excitation here given, which can be a sine function or which can be a cosine function, right? So these functions are going to give you, if it is referred with the function of x, the road profile is like that. I have n number of road profile like that is combined is what is referring to random nature of road profile. So if you look at here, I can see this is my amplitude of road. If I say at any distance, I would be able to say by what is the value of my road elevation. If I have one deterministic function like that, if I excite my road. So base excitation for singly repeated model we have seen by harmonic excitation. So what is that is a deterministic model where I am certain with at any point of time in the road or any point of distance in the road from a reference, I know what is my elevation profile. But in real-time road, it is not so. I can't say from Katpadi, I just get into highway. So from the start of highway at 10 meters, this is my elevation profile, and 20 meters, this is my elevation profile. You cannot say that. So that is what is that can be described by random function. So we are going to look at how this random function can be modeled and handled is what I'm going to teach, right? So let's proceed with that. So what is our ultimate aim of this? So what are that we are doing in this deterministic model? The deterministic model, whatever that we do is we find out the response of your vehicle, sprung mass or unsprung mass, or for a detailed experimental study with the seat pad accelerometer, we found what is called an RMS acceleration value. So the RMS acceleration value is what is the measure to say your comfort. That's what we have seen in this standards. Look at here. So this all on this y-axis is the ISO 2631. What is having is RMS acceleration. So we have to get the RMS acceleration. To get that RMS acceleration, what you require is the characterization of your vehicle through its power spectral density function. So this is the formula for finding out an RMS acceleration. And you see here it is an integral, goes from 0.89 FC to 1.12 FC. And this is what is called the power spectral density function. Function of vehicle vibration. So what is this power spectral density function? How do you get that? Let's understand. So if you know this power spectral density of your vehicle vibration, if I integrate this from this, where this FC is what is called central frequency. Like in one of the class, I was telling you that in the beginning class of our module 1, instead of representing a variation of frequency on your horizontal axis, if you are representing by its band called an octave band, that's always good. So that's what we have seen. There would be, instead of an absolute value, you will have an octave band, and every band will have one central frequency. So you'll have a lower and upper limit. So the limit, the ratio of upper frequency to that of lower frequency in a range is what is equal to 2 is what is called an octave. And if that is going to be 1/3 of 1/3 of 2 power no, cube the root of 2, then it is called in 1/3 octave. 1/3 octave. So 1/3 octave bands are generally to have a wider frequency excitation, and then you would say your SV of F or SV, this power spectral density function of vehicle or from the road profile, all as a function of bands. If you are saying, that is very good. So that is what you would see. If you have this function and if you differentiate, if you integrate that this interval and take integrated, you'll get mean square value, and take the square root, you'll get an RMS acceleration value. So now in our lecture, this first period, we are going to look at how do you get this SV of F and its significance and so on in more detail. Right, so look at this. Why do we do again as all for this human response to vibration? Already we have seen, and the exposure limit given by 3 standard exposure limit or proficiency boundaries or reduced comfort boundaries. So these all are going to emphasize more on this RMS acceleration. That's why I just have again put this in this. And you see here is a case study of a vehicle ridden at 80 kilometers per hour on a smooth road. So you say, then what is smooth road? So how do you define smooth road? All we are going to look at in today's class. So that these boundaries are for your vertical as well as in lateral AX and AY, and this A is at 1/3 octave band. So look at these are 1/3 octave band variation and RMS acceleration values, and these dots are an actual values of measured which are below this ISO 8 hours boundary line, and also it is for reduced comfort boundaries. So this graph is what we have seen in a previous slide. These all are brought down by 10 decibel level down. So this is that the case study problem you could see. So if you got your RMS acceleration for any of the frequency of excitation that comes from the road, your vehicle has got a good level of comfort. Can be concluded from this graph. And that is what is measured through this kind of instrumentation. And we are going to look at this RMS acceleration. How do you get it? So for that, I'm going to take a simple case to understand the concept, a single degree freedom model. When I say single degree freedom model, your entire vehicle can be modeled here. This is the car mass. It's not only MS or MES, it's combined, the car mass, correct? And I take an equivalent spring here. So equivalent spring, when I say it is accounting suspension spring and tire, and an equivalent damper here that accounts all like that if I have. And I have my vehicle single degree freedom model. So if I have the single degree freedom model, I give an excitation here, and I can have my bounds given by this. So what is that I get here is something called a transmissibility ratio that you have seen. So that is going to be Z2, sorry, here is it Z1 vehicle body. So let's take Z1 by Z0 is what is this, and you have a variation as a function of frequency ratio, which is well known to you. Can we look at it? So what is this called? A transfer function or a frequency response function, defined as the output to input under steady state condition, is what is this plot for a single degree freedom model, and H of F is what is this for a function. And when I have my displacement amplitude for a given displacement road profile Z0 and is it Z1, then I get what is called this through this function, my transfer function, which is there here, which describes the vehicle system. And you see here small f is what is called frequency of excitation, called a temporal frequency of excitation. F is what is given by omega by 2 pi, right? You know that. So this can be varied, and Fn is what is referring here is your natural frequency of your vehicle body. That is Fn. So you can consider here the second formula. I just have taken this number as it is, so that's convenient for you to go through the textbook and look at the equation easily. right? And it is multiplied by with this 2 pi f whole square. It's because you give a road profile elevation and you get your response and acceleration, then your transfer function to be multiplied with this factor, omega square factor, right? Yeah. So, and you can see here the role of your damping that makes at the uh, frequency ratio 1. That means your F is closer to or equal to Fn of the sprung mass frequency. You have to require really a help of a damper to attenuate this amplitude. If you do not, then it would have a severe problem of breakdown of your vehicle. So that all we have already discussed. Of course, if you have higher damping, that is to have some penalty at the high frequency ratios. But the high frequency ratios, you see, they are already below this. This is a log scale, so it will be a fraction of energy only that enters the vehicle. And the isolation is well uptime. So that is what was the design of your vehicle with the 2-degree freedom model we have seen, where this can be MS, and I have its natural behavior to do with the spring connected to unsprung mass. This is a suspension spring, and this is MUS, and then the tire over this. So when it is naturally disturbed from its mean equilibrium position, I could see that this would have around 10 hertz natural frequency vibrating, whereas this would have 1 hertz. So they are well separated, and when most of the energy is occupied by tire wheel assembly and it is hopping with this resonance closer to resonance, the energy enters here would be very less. That's what can be witnessed in our study. Already you have understood that. So in the simple linear vehicle model of single degree freedom, what is an input to this vehicle system? So when I say vehicle system, your model or your experiment, in experiment you can give a known input excitation through what is called a model shaker, and then get your response, target response, and you get your transfer function. In this case, you get through a single degree freedom model. So simple, this equation acts as your transfer function. So that describes your vehicle nature. So we are good at understanding vehicle nature through this model. And surface irregularities are given again like power spectral density function of your ground in temporal form, F, right, as function of F. So if I have this as an input, and if I give this as an input, I'll get an output here, and that would be my SV of F. If I know my SV of F, I can get my RMS acceleration very easily with this formula. So RMS acceleration would be simply integral, goes from 0.89 FC to 1.12 FC SV of F into df, and take the square root of this all, that gives you this. So that's what easily can be applied. So let's now look at how do you get this SV of F. So for that, what to do? How do you understand our road profile? So I'm going to explain you that. Also see that here in specific, I have this quarter car model. So you can see here the importance of damping. So you have the damping value low, that is not preferred at your resonance of your sprung mass. Of course, at the resonance of the unsprung mass, it's insignificant. Whereas here it is important that you are preferring high damping value, but that is not good for your other range called mid-frequency range or high frequency ranges. So if you look at for your ride concern, the variation of transmissibility function as function of frequency ratios or function of frequency here, it's not a ratio. So what is that you get as 3 regions. One is below the resonance called low frequency and mid frequency and high frequency. So at low frequency as well as at resonant frequency, you require high damping, whereas that's not preferred at the rest of the range of frequencies. And that is what is this requirement of your shock absorber. But once you design yours for this, and this has to be penalty or compromised. So that's where the role of semi-active or active suspension system that comes into picture. We will see that in second part of our lecture. in detail, right? So let's take this back again and do it later. So what is that we are going to have it here is interested is this, what is this RMS acceleration? RMS acceleration of this MS. So this is what I am interested in finding out. So and in fact, this is again a revision what we have done in the previous class, classical vibration analysis of quarter car model to get your amplitude ratio. This is what is transmissibility, right? Z1 by Z2, or Z0 to get this. This equation we have seen, you have asked also this doubt in the class. I clarified. This will go ahead with this. I'm getting back to the slide of our focus of getting what is, how do you get this SG of F? This is what I'm going to explain you in coming slides. So if you look at, if the transfer function of the system is known, that is SG of F is known, in general, the relationship between the input of the system, which is ZG of T, this is given here as function of T. You can also have as function of T, you can also have as function of frequency. But having them as function of time, as having them as function of frequency has got its advantages. When you represent them in frequency, it's just multiplication. If it is in a time domain, then it involves a convolution integral and so on. So that is on other part. Let's proceed to look at it. Right. So I have in this way. So if I multiply my road mean square value with G of T with the transfer function, I'll get my vehicle mean square value. So how I get it in the frequency domain is this analogous equation. So this is in time domain, this is in frequency domain. So what is this SV of F? SV of F. SV of F is this. So this SV of F to get, I certainly use this SG of F. So SG of F is characterization of your road, and this is your vehicle system, right? So this indicates that the power spectral density of output SV of F is related to power spectral density of input is G of F. So from this, right, through the square of the modulus of transfer function of a linear system. So this is all for a single degree freedom system that we are looking at. So if this is that you understood input multiplied by vehicle system nature, you get your output, and you get the power spectral density function describes the road is known as an input. You get what is that is for your vehicle, and that helps you to get your RMS acceleration. So how do you represent your road elevation profile? So it's very interesting. That's what I was telling. Earlier models we have studied with the deterministic function, harmonic functions, or it can be a step function, it can be of triangular function, where we have some formula and then you are able to give it. So what do you mean by that? At any given value, whether it is a function of time at any given time or it is function of space at any given place, you are able to say the value of the function, but that's not explicit or readily in your road profile. So what does this graph refer? So there is a reference plane OXY. So OXY is slicing up your road with a perfect smooth slicer. So if I slice it and then take my road and then I weave my road, keeping it in front, there will be a variation of my profile. So here there is absolute zero variation in this plane, that's a reference plane, and over which I have my variation of my road profile given like this, and A, B, C, D are some of the points, locations in this section. So like this is one section in a reference plane. And similarly, if you look at, I have another section A dash, similarly B dash and C dash and D dash. So I have another section like that. I can have n number of sections in lateral direction of the road, and X is the longitudinal forward direction of a road. So when I say this road, it is our highways. If I take a small patch along the forward direction of my vehicle and I slice in the lateral direction my roads, I can look at the variation from an absolute reference plane where it's zero elevation. So this elevation is measured. So that is what is called a surface elevation profile as a random function. You can say, if I say here this value of A, I can't say this value of A at this distance X is this much with one function like a harmonic function. I cannot say that value of B is this much at this distance. I cannot say. That's what is the nature of your or character of your random function. So then the question comes, how can I then make use of this? That's what is through statistical measures. Statistical measures. So what are statistical measures? Mean value, mean square value, or something called an autocorrelation function. Right? And then you have a higher order statistical parameter, cortices, and so on. There are many of them in statistics. If you look at, if you have a data and the data mean value would be a good measure, or mean square value is a good measure, or an autocorrelation function. What do you mean by autocorrelation function? If I have at one point my value and what would be its value with respect to the previous value. That's what how it is correlated with reference to A, B value with reference to A, or C value with respect to B. If I say, that's where I define what is my autocorrelation function of that individual. So if I have such kind of measures, that is quite sufficient to account the road and take that road as an input to our vehicle model. So this road profile can be represented by random functions, as we have seen, and can be called a stationary function or ergodic function. When can I say this is a stationary function and ergodic function? If I calculate mean value of this patch of section where I have the patch observation from A to D, say. So if I have my mean value between A to B, so I have my all elevation, just add all of them and then divide by number of samples. That is what is mean value. So take every value square and then add and then take an average. That's what is mean square value. So this is all have been done by an averaging principle. So if I have my mean or mean square value or autocorrelation function between the data taken from A to B along the length of the road in this particular section is same between B to C or C to D, then I call that road profile a stationary random function road profile. If that same, the mean between A and B and A and B dash is same here, and any section parallel to this section, then it is called an ergodic function. So our highways are laid, the international highways are laid so that they can be best approximated by stationary ergodic functions. And then that analysis become very simplified to a greater extent. So why I was harping on this stationary ergodic signal is because, see, I had happened to listen to a colloquium of Mr. Prashant Pawar from ARAI, and he is a PhD scholar, external PhD scholar of our university, working under Professor Arun Tom Matthew. And last 4 or 5 days back, his colloquium. He is pursuing his PhD research in characterization of road and estimation of road roughness profile. That's called an international roughness index. So he is estimating that for an Indian roads. So he has made a huge measurement because the authority of our automotive field, they have very good facilities in their project. They are able to make a measurement from south down to up north on the highways, and they are going to have different. He has presented in 4 nice modules this presentation. So he's only working on characterization of your road, and that's what we are seeing it in a few seconds, a few minutes in our lecture. So see that how the research is going on still to have your road nature to bring in a mathematical form that would finally help us to do a real-time scenario instead of really carrying out for every vehicle on the road profile. So when this statistical measures, as I have said, going to be as stationary ergodic nature, then I don't require my vehicle to be ridden for many hours, few seconds sufficient. So that is what is the basis. So our hostel side B block road is assumed to be of stationary ergodic signal. I just measure some 30 to 1 minute data, and that's more than sufficient to say what would be my RMS acceleration pursued by the occupant inside, and I can extrapolate for 1 minute exposure or 8 hour exposure all. So that is what is the beauty of having this kind of approximation of stationary ergodic signal. And you know what do you mean by stationary signal and what do you mean by ergodic signal of a random function. And these statistical parameters, what are there here, is basically determined by the principle of averaging, and the frequency content here are through a Fourier transform. In mathematics, we have this Fourier series and Fourier transform. Fourier series to account the periodic functions decomposing, and Fourier transform is to have a random function decomposing, and you are able to have you are able to represent this road variation as a function of spatial frequency, as a function of distance is given here. You can represent that as a function of spatial frequency. That is how many cycles per meter nicely by help of taking Fourier transform of such profile variation as function of its distance. So that's what is the beauty of this mathematical tool. There are filters based on this Fourier transform. They automatically does when you have this profilometer data. And then you would be able to do it. So that to understand, let's understand now the amplitude of surface profile. So when I say amplitude of surface profile, when it is random and you are decomposing them into number of wavelength. So I can have a wavelength like this. I can have a wavelength, another one can be a longer wavelength. I can have a very small wavelength, right? So it will vary from micrometer to mm or even meter on a highway, and that is how that's put. So these all wavelengths are bunched together, and that become a random. So when I add all of them, that's become random variation like this from the reference. So this is my elevation profile, what you are seeing. So here, what is that I'm having here is this as function of spatial frequency. The cycle from by meter. So here what is there is amplitude. So the amplitude can be small, amplitude can be higher, and this wavelength can be, this is what is wavelength. This is what is wavelength. So this all are what is characterizing your road profile. When I decompose this, I can have like this all. I can have my wavelengths of smaller micrometers till wavelengths of centimeters. And when they are decomposed like that through a Fourier transform, I would be able to represent the amplitude as function of wavelength, not as a spatial frequency. They are inversely proportional, correct? So wavelength, then what will happen? I take a wavelength instead of an absolute variation, I take in a band, and that what is going to be like that. So what you observe is as the wavelength become higher, your amplitude is going to be high. That's what is the nature of your road. If wavelength is smaller like this, the amplitude is going to be smaller. So that's what you understand. So you take with the central frequency wavelength, central mean wavelength, and then you have this, and then the fit of that is what is this 9. So the reciprocal of that would be with the negative slope, right? So then the amplitude variation as function of spatial frequency can write. So that's the basis, and that's how you should understand our road profile, right? So you do not have the road in a sequence of wavelength smaller first and then the next, not like that. All are bundled together, and we do not able to distinguish these amplitudes and these wavelength as we measure, and that will be like that. And only statistical measures can be helpful, mean and mean square value or autocorrelation function. But for an analysis purpose, I can decompose this all into a standard wave forms with the different wavelength and amplitudes as function of circular frequency, spatial frequency. This is called a spatial frequency. So there's another called a temporal frequency. We'll see that. Right. So having understood this, now we can understand what is mean square value. So in random vibration, the mean square value of amplitude and not the value of amplitude is of prime interest. So mean square value is what is important. I'm not so much worried about what is my amplitude value like that. Since it is associated with an average of energy, so we will always see what is the energy that is coming to the vehicle instead of saying what is the amplitude every time it comes. So that's a good measure and sensibly to account. So the harmonic component of Z n of x. So there are n components like I have shown earlier. That's nth component would be a harmonic component with an amplitude nz, and the wavelength is L omega n. If I say, I can represent that function as this. So what is that function? Is this sine function, right? So here, what is omega? This is omega into x in this, and this is my amplitude. Amplitude is Zn. So in this case, it is Zn, and this is that. So this is the variation omega x into x. I multiply, I get this. So this is what is the function. So you see here, what is this? Is 2 pi x by L omega. So 2 pi by L omega is what is spatial frequency. So I had in earlier case road profile as function of wavelength. So 2 pi by wavelength is what is spatial frequency, and multiply with the distance. Like omega t you put here, spatial frequency time x here to put. So that is what is going to give you my nth component of harmonic, nth harmonic component. Like that, one second, n number of components I have. So if I pick one arbitrary nth component, I can represent that again now with the deterministic form of a harmonic function. If that is so, I know here what is omega x, that is 2 pi by L omega n. Like temporal frequency 2 pi by omega, you write the circular frequency here. The spatial frequency would be 2 pi by wavelength L omega n, right? Of nth one to get. This is the circular spatial frequency of the harmonic component expressed in radians per meter. Look at radians per meter and SI units. So the mean square value of this component, now I can easily get it through this integral from 0 to wavelength, Zn and this function square dx, and that would be resulting in Zn squared by 2 is what is the mean square value of my function Zn bar. The bar refer here is mean value, and square refer to mean square value of this. So amplitude square of nth component by 2 is what is the mean square value of my nth harmonic component of my random road profile. If that is so, you can look at now, I have that spatial frequency instead of 1, I have a central frequency omega naught and then its multiples. And with the range of delta omega, that is upper and lower frequency difference, spatial frequency, this is spatial frequency if I take, and my mean square value would be different for different central frequencies. So it's not a constant, it is slower here, then it's decreasing, it will be like this form. So if this central frequency range delta omega is going to be shrink, what will happen? This discrete value variation of mean square would become continuous variation, and that continuous variation would be what is referring to power spectral density function, right? So you know what is now power spectral density function. How do you define power spectral density function? Is it's a mean square value when you look at in a discretized spectrum of a random function, you would have for an every central frequency a value. But this central frequency is going to be very close by close. When I reduce this delta omega tending to 0, what would happen? This become a continuous function, and the variation would be like this. And the area under this curve is what is going to give me mean square value. And this function variation is what is called a power spectral density function. So when it is continuous, that's called a power spectral density function. The density word is because the power per hertz, that's the meaning. And here you see mean square values given here. So this is discrete frequency spectrum as a random function, and here it is a continuous power spectral density function. So having this power spectral density function, and from one point to other point in this spatial frequency, if I integrate, I will get this area under this curve, and that is what is going to be my mean square value. Mean square value. Right, so this is what is the power spectral density function definition, and there is a digital spectral density analyzer, which is basically working on the principle of Fourier transform, and there are different band filters, and that is essentially going to give you this values calculating. I will leave it to you to read yourself, and let's continue. So if you understand what is power spectral density function, and I have that in a continuous domain, and it's integral from one point to the other frequency range. It gives me the mean square value. I can always represent my roads with this power spectral density function. So look at here these graphs. There are 6 road profiles here. So on this left graph, I have a smooth runway of an aircraft runway, smooth highways, and then you see rough runway. So this 1 and 2 is for runways which are smooth and rough, defining in a different spatial frequency range. See, it's 0.005 till this, or it is 0 to 0.5, 05. This is 0.058. It's on log scale, maybe it is 0.067 something. So cycles per minute. So this is spatial frequency in SI units. Let's look at an SI units here. So for this range, you have a smooth runway, and this slope defines your power spectral density function. So these are obtained through the experimentation, right? So this is the definition of your smooth runway. If I have this variation as it is, I can have my road input. And on the other hand, again, the number 3 and 4, smooth highway and gravel road. So gravel road accommodate wider frequency range, and smooth highway again for this frequency range. So when I say smooth runway, it's a very low frequency here. So the spatial frequency. Let's first understand how do you get conversion of frequency to a temporal frequency and spatial frequency. If I have spatial frequency, if I multiply by velocity of my vehicle, I'll get a temporal frequency. So temporal frequencies are in hertz, otherwise called cycles per second, and spatial frequency is in cycles per meter. So if I have this multiplied by meter per second, meter goes, and I get a temporal frequency. So this is what is in our study that we are looking at it. So if you want to get your horizontal scale, which is spatial frequency, to your temporal frequency, multiply with this vehicle speed and look at it, you have your temporal frequency. So the variation of your power spectral density function, you would get it as function of temporal frequency. And here on the right side, again, you have other two country roads. So one is plot field road and pasture road, and their variation that accommodate from smallest till the higher frequency spatial ranges this road. So this is one way of referring road profiles. So you look at the road profile. Another way is to look at road texture, and essentially that is an roughness index. So International Roughness Index, IRI, that's what I was telling Mr. Pravar is working on. And you see here how these are quantified. So power spectral density function as versus spatial frequency. So this is the equation you can see. The road data, SG of omega, what is that you see here? It's all line. So you may ask, how can I use this data? So for that, you have this table and this formula. So these 6 roads are now given by this formula, SG of omega here, that's equal to CSP omega power minus n. And you are described all the 6 roads here in this table 7.1, smooth runway to this all. So there is the n value of this formula, that's a curve fit. So this n value happens to be 3.8, then the first road is represented. If it is 1.6, then the 6th road, plot road field is represented. And you have the CSP coefficient value given here is for an SI units, and given here SP dash is for to get it in feet square per cycles per feet, right? So we will focus on this two data. So having this equation SG of omega, putting this value here and with this exponent value here, and I would be able to have generate varying this omega my row data. And you have it in an Excel sheet, and take the data to your quarter core model and you excite it, you would be able to see the wonders. So you would be able to do a parametric study of running your quarter core model on your smooth runway to your plot field runway, and you can have a good parametric study. This can be taken as a project case study work by any of your interested, right? So this is how you can represent your road profile as a power spectral density function. And if you have power spectral density function, you can have always your vehicle power spectral density function, because you are characterizing your vehicle with this transfer function called the frequency response function, and multiplying this SG of omega with that, and you would get your vehicle power spectral density function, and then you put that in an integral of 1/3 octave band, and integrate and take its square root, you get an RMS acceleration. That's the fundamental. So the other way of representing your road roughness is this. Road roughness is by ISO. So you have a classification of road surfaces from A to H. So that means very good road till the poorest road. And you have here this degree of roughness given by power spectral density function of your road multiplied by, see, there's a factor 10 raised to minus 3 meter square power, that's why it's meter square, per spatial frequency, that's a cycle per meter. So if I have this divided by vehicle velocity, I'll get a variation of this as function of temporal frequency. That's it, right? And you have this road is classified for two ranges of frequencies till around 1 hertz. Also here you have that's not 1 hertz, it's 1/2 pi cycles per minute. It's not hertz, it's in meters, right? For wavelength up till this, or up till 1/2 pi cycles per meter, spatial frequency, you have a range. That slope is different, and then you have this. So you are given the formula of omega. If it is less than this, you should use SG of omega to get by ISO road roughness value. You have to have SG of omega naught multiplied by omega naught per power minus N1. So what is this N1 and N2? So N1 will be 2 for the first range, and N1 will be 1.5 for the other range. So you have to know how to use this table and to represent your road roughness value given by ISO. So I think it's easy for you to go through. In case you find it difficult, you can always be back to me. I can explain you again, or listen to this video again. And then again, you see, there is an example here. I leave it to you to go through this again. And therefore, you are able to get, yeah, this is what I was writing. So if I have to get it in hertz, my variation of frequency, instead of spatial frequency, I have to multiply with the velocity of vehicle. If I do that, if I understand this relationship, and to get my road excitation ground as function of temporal frequencies in hertz, I have to get just to that whatever SG of omega from table 1 and 2, you get it, divide that by V, vehicle speed, and you get that, right? So having found SG of F, you have done your task. What is that task? SG of F multiplied by your H of F, which is your transmissibility function. Its square value here, its module amplitude square. This product is going to give you SV of F, and SV of F is put in your integral to get your RMS acceleration. So this is what how you would represent your real road as a random function, and to find out your RMS acceleration. And this lecture is, though appearing new to you, that you have not earlier looked at random function and so on, you don't need to worry about it, and go through this video again, or read the textbook one and get back to me. And this is very important. That's why always students ask, how can I model my road? How do I give an input? And I say it's through your power spectral density function. Those who have understood, appreciate and follow. Those who have not followed will stuck. But please don't worry, and feel also bad that you don't follow. Get back to me, right? Again, yeah. So with that note, let me just stop today's lecture, showing you this case study. Now you would know what is that I'm all talking about. These dots referring to an RMS acceleration as function of 1/3 octave band when it is written on a road profile, particularly on a smooth road. When I say you know what is smooth road, now you are able to immediately get back to this here. You see there is a smooth highway referred here, so you can take either this or you can also be taken from ISO roughness values. So for that, when it's done, your RMS acceleration calculator all falls below this value recommended for reduced comfort boundaries, and that says that good ride is achieved. So here on this left graph is that what is the perception of RMS acceleration from foot to head, and on the right what you have refer in a lateral direction. Either it can represent what is from back to the chest or from side to side of a driver or occupant in a vehicle by ISO 2631. So with that, I'll finish this first lecture, and then we will get into the second lecture. If you have any doubts, please ask me at this point of time. The second lecture is just in another 20-25 minutes. I can finish it. That's just an application only. If you have any doubts, please ask. Otherwise, I would stop now. So, is that clear? Or was it clearly reached you? You have understood? Any response? Yeah, I take granted that you understood, and I go ahead and stop at this point.